Has this ever happened to you? Having to go outside on a cold day only to find yourself horizontal on the ground? Or what about this? Having to shovel early in the morning only to start off your day with a face of snow? Fear no longer. Introducing the Assault Robot from ICE. Skip the dangerous commute down your driveway and clear the ice from the comfort of your couch. Say hello to your new winter best friends. We are the Innovative Clearing Experts, a team of engineering students from the University of Colorado Boulder in Gene 1400-010. Let's meet the team now. Hello, my name is Max Paul Subramaniam, and I'm a freshman in aerospace engineering.
Hello, my name is Evan Fisher, and I'm a second-year mechanical engineering student.
My name is Andrew Toto. I'm a freshman in civil engineering.
I'm Jacob Vermeer. I am a freshman in aerospace engineering.
We are an interdisciplinary team with a diverse set of perspectives which allows us to bring a new approach to problem solving.
Today's ice melt is incredibly toxic. Existing systems drastically oversalt our infrastructure and natural landscape, dumping copious amounts of salt onto roads and sidewalks, and thereby putting dangerous levels of chloride into freshwater ecosystems as that salt runs down drainage ditches or seeps into the groundwater. Nationwide, 29% of urban streams have levels of salt exceeding federal safety guidelines.
But this excess salt affects us too. Salt is corrosive, and that spells bad news for our roads, metal bridges, cars, and other infrastructure, which tend to pick up that salt after it is spread. This can lead to shortened lifespans, and in the worst cases, even collapse. But even this fails to mention the thousands of dollars in liabilities for unsalted sidewalks. According to Boulder Municipal Law, Section 8-2.13, property owners must salt their sidewalks within 24 hours or face liability. The CDC estimates that slippage on ice and snow costs $50 billion yearly in medical expenses, some of which you could be on the hook for.
The Assault Robot solves these problems by limiting the amount of salt dispersed while fulfilling the legal obligation, thereby saving you money. It is also driven remotely to avoid user injury. The target market is people who live in areas like Colorado where it snows often while staying above 15 degrees.
The Assault Robot is comprised of many different systems, each of which have a large part in its ability to effectively function. We are going to start by exploring the wheels, as these form the foundation of the design. The wheels of the Assault Robot are designed to maximize traction and stability on all terrain. At 8 inches in diameter, they are big enough to pass over almost all paved surfaces, from cobblestone to pavers, with ease. To maintain traction, the wheels have embedded treads to dig through ice and snow. For smoother surfaces, there are rubber rings wrapped around each wheel. These factors create the ideal wheel design. Although the wheels are important, arguably the most important component is the dispersal system. Our dispersal system is a large 3D printed bowl, made of the same high-quality PLA as the wheels. The bowl is spun by a dedicated gear motor, which creates a radial force on the salt in the bowl and sends it cascading out the side holes. The motor operates at a max speed of 160 RPM, ensuring the salt stays on the sidewalk or driveway. Moving on to the drive system. Our drive system utilizes 2 brushed DC motors from Palalu that offer a max speed of 87 RPM and a torque of 4.2 kg/cm, giving the Assault Robot a max speed of 2 miles an hour. The motors are mounted in a custom-made motor mounts that were press-fit to size through the use of a Dremel. Initially, the system was reliant on tension belts. This belt-based system ultimately failed as we were unable to get sufficient tension to spin the wheels. Following this setback, the drive system was redesigned to be a direct drive from the motors.
This change in drive system required a change in body design. Our first design was very large, but we were able to pare down the size on our second and current iteration. Manufacturing our own body also gave us a chance to use our new skills in the machine shop and at the laser cutters. Our final design was assembled out of laser cut pieces of wood that linked together without the need for fasteners or glue.
Mechanical design is great, but it is useless without the proper circuitry and programming. The Assault Robot is run by 2 Arduino Unos. On the internal Arduino, a motor driver from SparkFun, a radio receiver, and the dispersal motor are connected. The motor driver gives us full control over the motors in both speed and direction. For our power system, we use 2 A23 12-volt batteries wired in parallel for the motors, and 4 AA's to power the Arduino.
Our controller is a simple wooden box with an Arduino Uno inside. This is connected to a wireless transmitter and a PS2 joystick module that allows us to control the speed and direction. We're using a 433 MHz wireless radio communication to control the Assault Robot. The first of 2 boards we received was missing a resistor after a botched soldering job, and therefore became dysfunctional. After replacing the board, the system worked perfectly.
With all of our individual systems working, we moved on to full integration, which proved harder than we had anticipated. In order to achieve our goal of not using glue or screws for the body, our tolerances had to be quite tight. This proved to be an issue as it became very hard to disassemble the robot after the first assembly. In addition, we did not initially have access to the electronics after assembly, so we drilled out 2 holes in the top panel as access holes. We were all very happy with our final product and learned a lot in the process of designing and manufacturing it. All told, the manufacturing of our robot ended up costing us about $230 to produce, leaving us with an excess of $70 from our initial $300 budget. By far our largest expense was the Pololu motors. We kept under budget by utilizing our resources at the ITLO. Additionally, the cost was waived on some of our fabrication requests as courtesy for failed prints. Thank you, ITLO.
This project in class definitely allowed us to expand our skills and knowledge as budding engineers. Each of us participated in workshops offered by the ITLL, including laser cutting, 3D printing, Eagle CAD, and saws and drills. These workshops gave us the tools we needed to accomplish our mission, and we're very grateful for the ITLL for this opportunity.
In addition to hard skills, we also learned some valuable ideas. The biggest lesson we learned was the importance of rapid prototyping. We kind of put all our eggs in one basket with the initial design and didn't do nearly enough to actually build and prototype that design. So it definitely became a mad scramble when we came to find it wasn't going to work. If we were to repeat this project, we would likely place a lot more emphasis on quantity of prototypes rather than quality of our initial design. Additionally, we experienced some significant growth as a team, and over time came to understand each other's strengths and weaknesses. Knowing these helped us delegate work, support each other, and trust in each other's experience.
As far as future improvements to our design, we'd like to have used something like acrylic or Delrin for the body, as it performs better in wet environments than wood does. We also really liked our initial design with the belts and the gears, and if given more time, we would have likely fabricated the gears out of aluminum with a 5-axis mill. We would also like to create a more elegant design for the controller, possibly utilizing a custom circuit board.